Right. Yeah. So shifting the spell. First of all, why do we have such title? Stuff like math, right? But when I was thinking about Axiom of Choice, I was thinking about like Harry Potter movies. Like you have the stick and put some spell on something, because that's what Axiom of Choice is doing. Like sometimes you got some magic from nowhere. But first of all, let us do not follow this one. Jim,
I'm sorry?
do you know how to hide this one?
Oh.
High quality meeting controls.
Yeah.
Oh, sorry.
Go down.
Yeah.
Okay.
Oh, cool. Okay, now I learned something.
Yeah. Let's tell some story. First of all, in 1904, Zermolov formally stated that any state can be well ordered. Actually, that is axiom of choice. That's the definition. Yeah, it's not very clear, but axiom of choice, like you can make, you have like an infinite set, and then you can just pick like some elements from that set, like you have an infinite subset and pick one element to each set, which is not very natural. If your set is finite, that's very simple. And then, like in the 1910s, Borel developed the measure theory, which just aimed to define the notion of size, like you measure something and what is the size, something like what is a surface, what is a volume, and in higher dimension, because we can see only a 3 dimension. And then after that, there was Hausdorff. He discovered the paradoxical decomposition of two spheres. That means the sphere without the empty sphere, just the surface outside, and he was able to decompose it into two pieces, but is same size as the original using axiom of choice, which doesn't make sense, physically, but mathematically it makes sense. So, and after that, just Banach and Tarski, they extended the Hausdorff paradox into 3-dimensional space. And in 2024, Kenzie Dowdy, she's a student here, a first year PhD. You might know her. She wrote a paper about trying to see the application of axiom of choice in physical object, and that leads to a lot of contradictions. So yeah, her paper is like very good to read. Okay, this is another aspect of mathematics, which is the area of topology. So in the 30s, mathematicians tried to understand topology just using lattice theory. I'm going to explain what is a lattice later. And in the 50s, there was a guy named Marshall Stone. He worked on functional analysis, but just suddenly research chemical algebra by developing the Stone duality, which just relate algebra and topology. And that is the basis of what I'm doing, what I used to do. I'm not doing it anymore. And in the 70s, John Stone, that was a Greek guy. He developed the notion of locale, which is generalized space. But first of all, let's have some fun. Yeah, it's a little bit stressful here. Okay, so let's make some trivia. Okay. So your answer is like, who is this mathematician? That's going to be your answer. So he was a French mathematician active in the late 19th century, whose work was trying to classify surfaces and understand their shapes through continuous deformation while doing. So he invented what we call homotopy theory, homology, and fundamental group. It's like trying to understand holes, trying to count holes, which is not easy technically. For us, it's easy, like, oh, there's one hole. Do you have any idea of who's that mathematician? What? Fabrice? No. He's a French guy. He's very famous. He had a conjecture but has been solved in 2000s. Yeah, by a guy named Perelman. That's who solved this conjecture. Okay, surprise, surprise. Poincaré. Have you ever heard about this guy? He's a big guy in topology. He was one of the father. I mean, he's a Renaissance guy. He did physics, philosophy, mathematics. I don't know how you do it. Another one, a German mathematician, but he's very known, but every mathematician talk about sometimes. And if you ever like learn topology, he has a name on a separation in topology. Also? Yeah, I just said his name. Last door. Yeah. That is just before we're gonna show how to decompose if you have a ball and how to decompose a ball and give it into two pieces, but has the same exactly same size as the original. So first of all, you just take a ball and then this should have. Who has like a perfect circle if they draw? I that sounds cheap. Yeah. So we have, first of all, it's like counterintuitive, but that's how they did it. So I use this book actually. The proof is in this book called The P and the Sun. It's like you take a P and you transform it into sun. That's what they explain. So you take like a rotation. First of all, you take rotation on this Z axis. Let's name it tau. And then you consider this plane, the XZ, and you take this axis, which is just 45 degrees from Z in the middle of the X and Z axis, and you call this sigma. So those are like two rotations on the sphere, and it can be shown that those can generate has anyone did like a group theory before? It's just you apply many times the rotation, like you rotate. So if you rotate 2 times, that is still a rotation, right? So basically it's closed under rotation, like have the same structure. And if you generate these, you can find that, for example, I say plus like 1 degree, and tau, and sigma is just 180 degree. If you can see, if you rotate 3 times, you get into the same position, right? Like, so you have a relation. I will write it 1 just identity. And if you rotate sigma, how many times this one? 2 times, yeah, 2 times. Then you get to where it started. And you just take this group, and let's say this is G, and you just divide this group into 3 G1, G2, G3, and you do 3 sets, but doesn't intersect. And basically what you do is like you work on how to divide it into 3, and those action of group is applied to the sphere. So that's the first thing to do. That's what this explains. And then after that, you just take the sphere, and so I'm not gonna go to the proof because the proof is like 18 pages. I don't want to do that. But basically the idea is like you take the, how did you separate those and you apply it back. And then you have a decomposition. And there's some technique that they call equi decomposition. And there's some property used in axiom of choice, but give you two sphere but has the same. And then to get the, you take the decomposition with the sphere variety, and they call it thickening. You take from the origin and then you thick the ball until you come to the edge, and you just got into the problem. But our problem is like not really that. We're not interested. We're interested in developing a new math that is, but can solve the problem without the use of axiom of choice. So okay, to make things fun again, let's make some question. So this is a mathematician. He is well known. Like he is the greatest mathematician, if I don't say of all the time, maybe of our century. And he wrote a lot of things about algebraic geometry. He developed a new concept, and then he wrote 1,000 pages a biography of himself. I started reading. I'm in page 50 right now. I don't know when I will be in page 1,000. Do you have any idea who's that man? Any guess? Nope. That's
Is it sir?
yeah, he's in algebraic geometry. So pretending. Yeah. So yeah, he's like, there's a story about him. He worked 16 hours a day doing math for 10 years. And after that, he just withdrew. Like he said, I'm tired. And he become like, he was worried about the environment and the use of science into, military things. That's why I'm concerned of. But he's a great guy. So first of all, we need the notion of topology. Has anyone ever heard what topology is? Okay, topology is just topos, but means space, and logy. I don't know if I say it right, logy, but it's just the study of space. And here, I just wrote down the abstract definition, but you can think about space. Space is composed of points, and opens, but it's like the surface and the volumes around us. So if you check like your table, what you see the surface, and if you draw like a little circle, you can think of that as an open. So it's just a set of points, but you'll never see a point. There's a point. What you see is just open. So if you you draw two things in your table, and you take the onion, it's gonna be still there, like in the table. So technically, that's what you're doing. Like if you just think about the collection of subset of X, and you take the onion, it's still inside the TX for collection. And if you take like intersection, then it should be there too. It can be empty intersection, but the intersection should be finite. That's, you need to be careful. And then if we define what the notion of a poset is just take a set, just a collection of objects, collection that makes sense, and you wanna like order something in that set. Like we can do it if finite. Like I have a book here and I can order it. Like I want to put this first and this second. And just the poset is like a set with an ordering relation, but means each element is related to itself, and it is anti-symmetric, but means if A is less than B and B is less than A, the only possibility is that A and B must be the same. And it must be transitive, like if A is less than C and C is less than B, then A must be less than B. So you have a positive relation. Then we can define one of the lattice. So the lattice is just a poset, but you can take finite joins and finite meet. So what is joins and meet? So think about you have finite collection of numbers like 1, 2, 4, 10. And then the meet is just the smallest number in that collection. So it's going to be 1, because 1 is the smallest. And the join going to be the biggest number in that collection, and it's going to be 10. So it's like that. You have an ordering relation and you have a subset. So you just want to try to find what is the smallest and what is the upper bound. That means, yeah. So you can always do that if you have a lattice, like you have said, that you can just take the smallest and biggest. And then we say that a subset is filtered if you take 2 elements, then you can find a smaller element than the original 2 you take. For example, you take 3 and 2, and you can find 1. In subset, it's hard to see, but in set of numbers, it's really. So therefore, we say that a lattice is just sigma complete if it has countable join. That means you have countable elements, and you can say, oh, there's an infinite element, but you can find what is the upper bound, smallest upper bound, or the one that big, how to say, I don't know if big makes sense to you, like the biggest, find any element in the lattice. So yeah, it's really hard to see because it's infinite, it's not finite. And the sigma frame is just a sigma lattice, but you have, this is what I call meet, but that means you take the small of those 2, which of those is small, that's the meaning of a mean. So the result gonna be the small. And it is a frame if this gonna commute with the join. The join is just the biggest among those. So yeah, just commute. I mean, we say distribute, not commute. It's gonna distribute. So that is a frame. And now we are interested to define a measure. So a measure is just to define a notion of size. Like you want to define a notion of size. So it's just a function from a lattice to a positive real number, including infinity, such that the measure of the bottom of a bottom element, that means the measure of the smallest element must be 0, which is making sense in numbers. Like if you can measure 0, it's 0. If x is less than y, then the measure of x is less than the measure of y. It's like if you see 2 people, one is shorter and one is taller, and then you want to measure their height, and the measure of the height must be the shorter must be small than the tall. That makes sense, right? And the measure must satisfy these. This is a nice property. Like if you add to measure, it's just the measure of the join plus the measure of the mean. And this what we call continuity. So the mean, if you have an ascending sequence, but in a sequence but going up, like bigger and bigger, then the measure of join is just the supremum of the measure of x. Right? So let's have fun again. I hope this time you can see. So I'm sorry, all the mathematicians in the 20th century are almost French. I mean 19th century. So this is a French mathematician who working on measure theory. And yeah, he defined the concept of almost sure events, which is probability. Have you done probability? Like we always say something is almost sure if the probability that it's happening is like 1. And was among the first rigorously defined mathematical model of randomness.
Is it Galton?
Huh?
Is it Galton?
Bolton? No, it's not. Yeah, Pedro, you were doing measure theory. This guy, his name is repeatedly used in measure theory. Really? Really? There is the bag, and there's a set named after him, satisfying the sigma algebra stuff. Yes. Okay, at least one. Yeah, I mean, yeah, he was the one working on measure. Okay, we can keep going. So what do we call a finite measure? So a finite measure is just you measure the biggest thing and it has a finite measure. For example, I think the universe has a finite measure. Can you say about that? The universe,
The observable universe.
the observable. But we believe, yeah, the observable universe, you can measure it, you can say it's like million or billion of light year. That's the so that is the biggest thing on the universe. It's the universe itself. So everything in the universe has a finite measure because the biggest has a finite measure. And sigma finite, if we take some element in which the join is the biggest, we call it the top. And all the measure of those elements, but join to the top is finite. This doesn't mean that the top is finite, the measure of the top is finite, but the measure of each element but joined to the top is finite. And we call a measure co-continuous. It's the inverse of the first one we had. The measure of mid of B is just the smallest measure of any x in B. So it's a nice property if it is satisfied, but sometimes it's not. And we say it's probably sigma continuous if the measure for any ascending sequence, like a sequence that's going up, the measure of x mid that sequence is just the supremum of the measure of x mid y. And by complete means, and here I said I defined what is a sigma complete, but here I say just complete. So complete means you can take arbitrary joins, where sigma complete is like you need countably joins. And now can define what is locale. So I said for topology, topology is just you have, think about it, you have X and you have a topology on X. And this is a collection of subsets, but satisfying like you take the onion, like by example on the table, like if you take the onion, it's gonna be in the topology. If you take the intersection, finite intersection, it's gonna be in topology, and X is there. So a local is just a generalization of this, like you have a local X, and then it is equipped with a frame of X. So it's very abstract, you don't see it. So instead of working on the points, you're just working on the open and you take the frame. So you replace this topology into an abstract lattice. That's the only difference, and it's like a generalization of space. And continuous function is just a function, but preserve the but is like a frame. A frame homomorphism, that means preserve finite mean and countable joints, which is same as in topology, finite intersection and countable onion. Yeah, I define it as a sigma local here. And the subspace is just you take the inclusion map and it must be continuous. So it's like a projection from a frame, so it's more in algebraic sense. And the coframe is just you take the set of all the sublocal. So I will go back to this later. But we're gonna have another one. So this guy, he founds category theory. He's an American mathematician. Now we start in the 50s. Now the American mathematicians are doing all the things. Like the French time is gone now. And he worked on algebra, homological algebra. He defined if you take an algebra class, it's most likely because of him. He wrote like a huge book, like a survey on modern abstract algebra. Does everyone have an idea? No. His name is MacLean. I think you know him, Jim, right? MacLean.
I'm not that old.
Uh,
I know who he is.
yeah,
I've heard some famous stories about him too.
yeah. I watched this some of his seminar. He's a funny guy. Now let's think about neighborhood. So a neighborhood is like, how to say, can we translate into everyday language? The neighborhood is like we're living in think about living in an apartment, and the neighborhood is just people in the same apartment, or not in the same building, but in different apartment. That's it, right? So a neighborhood is like that. Like I'm here, and if I move a little bit, I look at a little bit next to me, that's gonna be my neighborhood. So here it's gonna be like I'm taking a sublocal y, that means the subspace y, and the neighborhood of y is just the open above it. That means the big open just above it. But I mean by above is like just bigger than it, the open bigger than it. And we want to define a measure on from sublocal, which is just the set of all subspace, and we define it as the infimum of the measure of the open, in which that open is a neighborhood of y. So we work on the neighborhood now, like to understand you, we just look at your neighborhood, like how they behave, and then all of your neighborhood, and then make it closer and closer and closer to you. So at the end of the day, we come to you. That's how I understand things. Yeah, but the question is like, is it a measure? So to answer that, first of all, we need to define a regular local. So I don't know why they call it regular. I'm just following their terms, but a regular means like you can think about points here and a closed subset here, but means you consider everything inside and the boundary. Then you can find two open. So the open, you don't consider the boundary. Two opens, but doesn't intersect. You can always find that whenever you have point and a closed set, but you consider with a boundary, then. So basically that's what it said if we translate it in everyday life. I don't know if that's everyday life actually. But the proposition said, but if you have a sublocal, then the sublocal is just an intersection of its neighborhood. If and only if the closed sublocal, and think about closed like you have a set and you consider the boundary. You got like a picture like this, and you consider the boundary, while open, you don't consider the boundary. I mean, that's technically not correct, but a way to picture it. So all the closed are just intersection of a neighborhood. And if a local satisfies this, we call it fitted, a fitted local. And if L is regular, a local is regular, then it's fitted. So actually, the Euclidean space, that means R3, the three-dimensional space that we're living in, it's regular because whenever we find point and we can draw like a closed and we can find open that doesn't intersect each other, we cover the both. So this is the big result that solves everything. So if you use a measure on a fitted sigma local, then the other measure is a measure on SL. SL is the set of all subspace. And we don't care about the two. Those are going to be used in probability later. maybe next year I will open those. But this is very important. So think about it, like our problem is like we were able to decompose the sphere into two parts, same as the original, because technically it's because we use the axiom of choice. And first of all, there are notions of subset but is not measurable. There's some example that's more abstract, like Cantor said, it's not measurable. I don't know if anyone can confirm that. I did measure theory last year, so
The Cantor middle third set,
yeah, Cantor said.
couldn't know if you assigned that as a problem.
Uh,
The Cantor middle third set.
yeah, I was ask these kind of questions.
Yeah, so yeah, the problem is like because of axiom of choice, we can extend any measure in Euclidean space in to measure some set but is not measurable. Which like you shouldn't measure those because those are not measurable. But here we define the parts of all a new way to define the measure on all parts of the space. So instead of subset, we say sublocal. And to prove that this measure can extend on all subset of the Euclidean space, we just consider the n-dimensional Euclidean space and take a big measure, but we restrict on the range, that means the open set of Euclidean space. So it is clear that any big measure going to satisfy this equality, that means it is invariant under application of Euclidean group. That means you make transformation like how to say, like rotation, translation, that is isometric, but something but doesn't change the length. You know, like I can move, but that doesn't change my weight or my height. I just moving around. I can spin, nothing change. It's still me. So that is like Euclidean group. That's how it works. And then we apply it. We take the outer measure, that means the infimum, into a subspace, and we use the definition that we did. And we just use the theorem, but we have first of all, by the definition of of measure, we have the measure of, if we have two things, one is big, one is small, then the measure of the big is larger than the measure of the small. That we have here, the definition. And here, since the Euclidean space is regular, so it is fitted, then we have this like any subspace in the Euclidean space is just intersection of its neighborhood. And then we have this equality. So it is really nice. And be careful, what we have here is just inequality. So we need to prove the reverse inequality to get equality. And yeah, using it again, since Euclidean group, that means if I spin like this, I can spin back and turn. So we always have that. Like if you do an action, you can reverse the action. So we just take the reverse of any action that we did, which is S40. And we have the inequality back, so it's really easy. So that means the measure, but this measure is invariant under what is it? Euclidean action, but on isometric action. So as long as all subset of the Euclidean space can be embedded in the sublocals, then that means we just construct a new measure. We construct a new subparts of the Euclidean space that is measurable. So, and as long as in my proof, which is very long and it took me a week to do it, in my proof, I didn't use any axiom of choice. I didn't use any contradiction or excluded middle. Everything must be constructed, and it's horrible. I miss algebra too. It's like you can use some contradiction and have a nice proof. But this one is crazy. So then that means you can define every subparts of Euclidean space is measurable. then you cannot do the decomposition. You cannot have from one ball into two balls. Like if you have a gold and then you just do some transformation and get two gold with the same weight. Now it's not possible. So we're waiting if some people doing that using like chemistry. I hope that is possible. Then we'll work on the math again. Yeah. So, yeah, I use this book. It's in the library. It's fun to read. It's very how to say, if you don't have any mathematical knowledge, it's still fine because it's explaining everything using words instead of equations and stuff. Yeah, I use my master project doing this. Actually, it's not my master project, but the local wasn't my master project. So that's how I come here. And I use this book, frames and local topology. And I use some paper, but talk about measure randomness. So our last trivia is like talking about the mathematician. But he's an American mathematician, Professor Clemson. He's a big guy, community algebra, and got his PhD. Can you guess who is it?
I think he's sitting up there in the room.
Okay, so we don't need any picture anymore. Yeah, so yeah, and this is an opportunity to thank Jim. For organizing this club, it's always fun and you can see new things. So yeah, we wanna shop for Jim, like give him a.
I'll get up and clap for him. Any questions? Yeah, questions?
So the locals are sort of like a generalization of topology, you were saying?
Yes.
So what does a local
Yeah.
like?
Look like.
No, what is it again? Sorry.
Oh, so a local is just set of opens. So think about it. In topology, you have points. In
Right.
physics, you have points,
Yeah.
like points of time.
Right.
But can you have the points of time? Like, have you ever seen a point? Like a
Oh,
point.
it's never seen like a
No,
point.
what you see is like just the small parts
Yeah.
of a surface.
Yeah.
That is local.
So you're, I know in topology you create open sets. So
Yes.
a local is working with those open sets.
Yeah.
Okay.
But the thing is like in topology you have points, then you create opens.
Points.
So yeah, points at topology, you did just open. But in local, you don't have the points.
Okay.
You just given like some collection and you call those collection, satisfying some property, opens. You know what I'm saying?
Okay.
Yeah, but in some nice local, you can come back to points at topology. But there are some opens but doesn't have any points. And that is really, and it's a non-empty collection, but has no points.
Oh.
Very interesting. Yeah, I did that homework 2 years ago. I was shocked.
So I'll add a remark. So the thing about the counter sets that y'all were talking about earlier, so you take the interval from 0 to 1, jerk out the middle third, open interval, and then the third, what's left over in the third, and so forth and so on.
Yeah.
And what you're left over with, so measure is sort of a generalized way to sort of measure lengths, but with more complicated sets. So if you sum up everything that you pulled out, it's an entire length one. So the length of what you pulled out is the same as the length from 0 to 1, right? But the number of points left over are in one-to-one correspondence with the real numbers, right? So the interesting thing about that when it first came out is that was a uncountable set. So the counter set is uncountable, but it's of measure 0, right? So it's got as many points as the real line, but there's no thickness to it in a certain sense. So,
Oh, thanks, Jim. I forget about it.
okay, other questions? All right, let's think for brief. This is next week's the last week of class. Ansa, I believe, will be speaking next week. We will have a substitute MC, but well, I might make it back, maybe not. I'm coming back from Kentucky that day. But don't forget, A week from tomorrow is the math in, so hopefully y'all will be there. It'll be better than banana ball. And other than that, so I hope I'll see y'all for last math club and, the math in on Saturday. Y'all have a good weekend.
I'm gonna leave the map in if you wanna hang out.
I would-
Thanks.
Oh, he just.